We're going to talk about pulsars, specifically about timing residuals. And probably the key word here today is on the first word, exploring. We're just exploring things here today. An outline, first I'll review some of the basic properties of pulsars and how we detect them. I want to talk about the pulse time of arrival. And then once we have a time of arrival, we can make models. And then we subtract the observed TOA from the model and get a residual. And then I'll talk about a source for getting residuals, the nanograv pulsar timing array, and then show some results from narrowband analysis. Some of this will be a bit of review and some will be new, but pulsars are these highly magnetized, rapidly rotating neutron stars. They're formed from the collapsed core of a supernova explosion. And what we see is this periodic short pulse of broadband radio radiation. The observables are the spin period and the period derivative are the two things that we can see. And from those two things, we can get a lot of information. We can learn a lot. The pulse timing is very consistent. Periods range from some pulsars are down in the milliseconds, a few milliseconds, and some of them are up in the tens of seconds. The propagation effects on these pulsars, there's a lot in between us and the pulsar, mainly the interstellar material, the ISM, and that disperses the waves, and we'll talk about that. There's also scintillation, which is the multipath interference, and then, of course, everything's in motion, so we have to worry about the Doppler shift. The Earth and the solar system's in motion, the pulsar itself was in motion, so you have to account for those things. Basic pulsar properties are shown in this, it's called the P dot chart, but it's the period and the period derivative. The period derivative is the rate of change. It's on the vertical scale, and the horizontal is the period. It's a logarithmic chart, but all the various pulsars are plotted here. And it shows things like the characteristic age, which is not the true age, but it is an indicator of the age of the pulsar. It shows the minimum magnetic field strength necessary to generate the pulse that we see, and the spin down luminosity. What we're going to be interested in here today are called the millisecond pulsars. These are older generation pulsars. They're stable. They're in the lower left there, circled, and these are mostly from binary systems. They call it recycled pulsar, where the main pulsar now accreted material from its companion star, and it's in a very stable pulsar. Dispersion was talked about a couple times yesterday. So yeah, the higher frequencies are detected before the lower frequencies, and that chart shows the same thing we saw yesterday, and you have to account for that, and then we integrate the pulses to get that nice looking pulse on the top of the chart there, and that's what we'll be showing. So I'm going to, I did want to mention on dispersion measure, it's proportional to the density of electrons along the column between you and the pulsar, and that density can depend on which direction you're looking. If you're looking up out of the Milky Way, then it's going to be less than if you're looking down the towards Sagittarius, towards the center of the Milky Way. You have a lot more electrons there. There's two main things. One is dispersion, the other one is folding. And the top cartoon shows a weak signal buried in the noise. And in the middle, we fold it, basically like folding up a stack of paper. We fold it at the desired period. The key there is, as amateurs, we are detecting known pulsars. We're quite content if we can get a known pulsar. We look up the published values for the dispersion measure and period. If you're looking for a new pulsar, then you're doing a blind search. You don't know the direction, you don't know how far away it is, and you don't know the period. And that takes a lot more compute power than we have. So we're detecting known pulsars. The bottom one shows the result. You integrate or add up all the little contributions until you get a pulse. The individual pulse is going to vary because of the scintillation and the dispersion. While if you average over thousands of pulses and get a pulse profile, they're very stable. At a given frequency, the pulse profile is very stable. And we can do this in the frequency domain or the time domain. This illustrates the detection process. On the left, you have the neutron star that's spinning, generating this pulse that we see. In Haswell, we're a Deep Space Exploration Society. We have a 60-foot dish, and there it's prime focus. So we'll have our feed horn up there. We can collect at say 400 megahertz or 1420 megahertz, have a feed horn. And then the signal comes down coax to the receiver. We're using, then it's kind of a batch process. We use a tool that the professionals use called Presto to do the dedispersion and folding. And then we can generate a profile that's shown in the upper right there, the averaged pulse profile. And for reference clock, we're using GPS. So we're doing all these things, except we're not actually measuring or calculating the time of arrival of the pulse. And so that's what we're going to kind of focus on today, is what is the actual arrival time of that pulse. And so we're going to talk about TOAs and residuals. Just some definitions. When they say regular monitoring of the pulsar rotation, that's for the telescopes we'll be using here, that's every few weeks or once a month. It means regular, and they're doing this for years. So for years, a couple times a month, they monitor the same pulsar. And then the TOA itself is determined by correlating an average pulse profile that you just measured with some template you have in your back pocket. And this template is a high signal to noise template that you've collected previously. And a key thing to keep in mind here is every single pulse is accounted for. So you line the pulses by phase, and that accounts for all the pulses. And then the residuals, just the difference between the observed and the predicted. The reason we look at these millisecond pulsars is they actually have a very narrow profile. They're not spread out, and they're very stable. So they're used for high precision timing. And then the other term, pulsar timing array, it's not an array of telescopes here on Earth like we think about. The array is a collection of millisecond pulsars spread across the sky. So when I say a pulsar timing array, it's these set of pulsars spread out. The time of arrival, the first thing we do for time of arrival, we have to convert. So at the telescope, we collect in topocentric time, which is shown there, T-topo. We have to convert that to the solar system barycenter. And these are all the terms you have to apply: the clock corrections, dispersion measure, solar system terms, all that. Something to keep in mind here, and this is what motivates using Bayes methods, is both the observations and the models have uncertainties. So we have to deal with all the uncertainties. At the left is just a snapshot of a TOA. TOA is nothing more than, it shows the radio frequency, a pulse time of arrival given in the modified Julian day, and then the measurement uncertainty. And we also have these uncertainties in the models. So we have to deal with those uncertainties, and that's where the Bayes methods comes in. I also want to note that the template matching to find the TOA is done in the Fourier domain, and that was what was started by Joe Taylor, I think, back in the 80s. So that's still the same way they do it. This is a fuzzy topic anyway, because this is all the disturbances to the arrival times. And I can just mention them on the end, at the pulsar side. There's obviously the rotation period and the derivative. So the pulsar is slowing down. There's timing noise. There's the orbital elements due to Kepler and due to relativity. Then in between us and the pulsar is the dispersion measure that measures that column of electrons, but that's not constant because the hydrogen clouds, the dust clouds, everything's swirling around, even the solar wind here in our solar system. So the dispersion measure is a variable, it's not a constant. And it varies over time and location. So they've developed models to account for the variance in dispersion measure. And then here, I think we mentioned you have the our own motion here around the sun. You know, so we're going to talk about modeling a little bit. George Box was a statistician. He said all models are wrong, but some models are useful. And you probably experienced that. Somebody else said the best model of a cat is a cat. You know, anything less is a compromise. So we're going to be trying to model the time of arrival, the residuals, and it's just a sum of the deterministic and stochastic terms. So the first term there is called TM, and it's called the physical TOA model. Well, that's all this stuff here, where I talked about the conversion from topocentric to barycentric. All of that just becomes this first term here, the TM. Then there's the dispersion measure factor we talked about. If you're trying to model gravitational waves, then you need to add in that model, and that can be deterministic or stochastic. Red noise is defined as this low frequency correlated noise. And it's very low frequency. The time scales on the order of weeks to years. And then there's white noise. White noise is something familiar to us because that's what you get out of your own telescope. That's the radiometer noise. And so each telescope, each receiver is going to have different levels of white noise depending on the receiver electronics and everything. So all of those things get rolled into the pulsar timing model. And this is just an example of it. So it's just a text file. You can edit it. It's just a parametric model because it's got thousands of parameters. Each parameter can be frozen or not. So frozen simply means when you get to this stage where you're trying to fit the model parameters to the data, some parameters you hold fixed and some parameters you allow to change. So this is where it tells which parameters in the model you are going to allow to change as you try to fit the data. The timing residuals, the cartoon at the left, let's say you're collecting today in session I, and you do your data folding and you calculate your TOA, and that's what's shown on the bottom line there. Well, you can't, pulsars aren't the most important thing in the world, so the telescopes aren't dedicated to them, and the telescopes have to do calibration. The telescopes can't see the pulsar all the time, so you come back a few days later, a week later, you do another observing session, and you do your same algorithm, you do the folding, and you calculate your TOA, and lo and behold, there's a residual. Your model predicted value is slightly different than what you observed. Yeah, so the residuals are the difference between what you observe and what you predicted, and it's always in excess of what you predicted. And of course, that gets the interest of the scientist is, well, why is there always this little residual? What does it mean, and what can we do a better model? The bottom chart shows how the residuals have been reduced over, this was a 20-year period. So this data is from Arecibo and Green Bank telescope, the 100-meter dish. And so it's showing in 1993 there, the residuals were around, they were over 1 millisecond. So the time scale on the left is milliseconds. So it's over 1 millisecond. Then there's gaps, and then they show decreasing. And then on the far right, the little black line and the orange line are, they're way under, a tenth of a millisecond. So they've reduced the residuals simply by improvement in receivers. All the improvement in electronics, going to wider band receivers on these telescopes have helped reduce the residuals. They're down into the tens of nanoseconds now, but the residuals are still there. So why study residuals, and what is this nanograv I mentioned? So nanograv stands for North American Nanohertz Observatory for Gravitational Waves. There are other groups. Parks has a similar group. Europe has a similar group to where you can actually go and get data and study this. So I chose this one because, well, that's where my tax money goes. So, and you might be wondering, how in the world did I get down this rabbit hole anyway? And it started last fall down in Haswell, where we have an open house, and we had a group of people there, and we had just changed. So we have a 60-foot dish, and we had just changed our feed. Ray Uberekin had made a 437 megahertz dual helical antenna, and it was for an experiment we were doing, and we were just tuning it up. So when we first put up a new feed horn or new antenna, we have to adjust the gain on the receiver, dial in the parameters, and so we use this Pulsar B0329 plus 54 as our standard candle to kind of calibrate and tune against. And so what I did is I ran a whole bunch of 10-minute collects at roughly 30 megahertz, And the Presto, this is the standard Presto plot. You'll see here a very strong pulse. This is the time and phase plot. This is a 10-minute collect, so it's 600 seconds. The pulse stands out very good, nice continuous. This is your reduced chi-squared, which is basically showing that your signal to noise ratio is increasing the whole time. So this looks very good when your signal to noise ratio is increasing. This is your frequency and phase plot. And in this case, I went right up the middle of the ham band. There's not many hams out there in Haswell, and it's quiet. So I just went right up from about 415 to 435 megahertz. This shows your dispersion measure peaked at the right value. If your dispersion measure peaks at 0, that means your signal's coming from your shack. You're not getting very far. And then this is the period and period dot, which very strong signal to noise peaks at the right period value. This is the published period value. And so, you know, after we'd collected these, and I got this one, I thought, wow, that's one of the better ones we've collected. It looks very nice and strong. And I realized, oh, this could be a high signal to noise profile that I'd read about to use for the template. So this could become a template if we wanted to do TOA studies. So I thought about it, because we do frequently observe this. We keep the data. We've got quite a few collections on it. But this particular pulsar is not a good candidate for timing. First of all, on our end, and we were talking about calibration yesterday, we have not done a good job of calibrating at the different frequencies. We're in the process of determining our system temperature now at 1420. But in order to do timing, you have to have calibrated data. The pulsar itself is mode switching, which means every so often the pulse is not a single sharp pulse. It's got a little spike on the one side, and it'll switch sides. So the pulse itself kind of wiggles and wobbles around. This pulsar has a high scintillation, so it's not the best one. Nonetheless, I tried it anyway, but it broke the software because we're a non-standard observatory. For tempo, you can go in and add an observatory. For Presto, you need to make some slight modifications to it, but I hate to modify software if I don't have baseline data for regression testing. So I thought, well, I'll just go on the internet and find some data. And that's what Nanograv does. I can get, you know, the observatories are providing all kinds of data for citizen science projects. So Nanograv, here's a cartoon of it. This is Earth in the middle. With the pulsars flashing around in this pulsar timing array. And their goal is to characterize nanohertz gravitational waves. So nanohertz means the wavelength is up on the order of years, dozens of years. And they do this timing of these millisecond pulsars. What they're looking for is a stochastic gravitational wave background, potentially coming from a binary merger of a supermassive black hole. So that would generate a stochastic gravitational wave that would affect all pulsars, say in the Milky Way. And then on Earth, we could detect that correlated signal. The signal would be correlated since it was a single event. It would be correlated. Each pulsar would be affected, and then that could be detected here. But beyond the gravitational waves, there's quite a bit of other science you can do. You can determine a better value for the neutron star mass. You can determine do some studies on the interstellar matter, the dispersion, the profile variations, test of general relativity. So is this chart looking all right now? So I am going to go back to an earlier chart because I forgot to say something that on this one, because we got off to a bumpy start. But on this one, I think I talked about it, the words, but I didn't talk about this interesting plot here. So before I've shown a cartoon from Wiki showing what an artist impression of a pulsar would look like, and it tends to have the magnetic dipole. You have emission in the north hemisphere and one in the southern hemisphere. So here's an actual simulation from some X-ray data. So using the NICER satellite, which is a NASA satellite, a NASA experiment to look at the interior composition of a neutron star. It's in the X-ray band, and this is on top of the International Space Station. So this is a nearby pulsar, and one of their goals is to do a surface map on a pulsar in X-ray. They get the data, and then they do a simulation back at NASA Goddard to match the data with their simulation, and this is what they get. Notice there's no source of emission in the northern hemisphere. They're both in the southern hemisphere, so that was an odd thing. And the other thing they've determined is that in some pulsars, the X-ray emission is not in phase with the radio emission, which means that they're at different heights in the magnetosphere. Whereas for other pulsars, the X-ray emission and the radio emission are at the same height. They're in phase, indicating they're at the same height in the magnetosphere. So all I was going to say about that is they're much like FRBs for pulsars. There's a lot that's unknown. It's still a mystery how the magnetic fields can generate these, and some of the things go on there. So back to where I was, we were going to look at the nanograv pulsar timing array. So the 12.5-year data is what's publicly released right now. The 15-year data should be available soon, but the 12-year data is what I used. Nanograv has 79 millisecond pulsars, and they're collecting from roughly 800 megahertz up to 3 gigahertz. And they try to collect every once a month or so. And each collection is about 20 to 30 minutes. Arecibo actually had 41 of the pulsars. Green Bank over here had 39, and VLA had a few. And this is just a sky map showing the location of these. Obviously, in the southern hemisphere, like Parks, we'll have a lot of them down here in the south. And then obviously losing Arecibo was a big hit on nanograv. That was a setback for them. So very quickly they were able to get Chime and Green Bank to take up the slack. So they've been able to continue the same pulsars they'd been collecting for a dozen years, except now it's more Green Bank, and Chime is picking up quite a few of them. I think their goal is to collect data for 30 years. If a wavelength is 30 years, they've only got half a wavelength so far, so they're only part way in. This is just a cartoon of the gravitational wave spectrum. On the right here is, on the top, this is milliseconds, and this is the wavelength. LIGO, the ground-based laser interferometer, has already detected gravitational waves in this frequency. And then LISA, which is the space-based interferometer, I don't know the status. I think they're working on it. I don't know that they've actually been successful yet. I think they're in orbit. Over here on the left is the CMB polarization studies that we heard about last year from Dr. Darcy Barron. She talked about the work they're doing to detect polarized fields in the cosmic microwave background, which would be the indicators of the Big Bang and of the gravitational waves left over from that. Then right here is what we're looking at. So the radio pulsar timing arrays are working in, so it's in the nanohertz frequency, which the period, that makes the period on the order of many months to many years, dozens of years. So this is the area we're looking at here. Just a mention about, the gravitational wave background is their main goal. It was not my goal. So I'll just mention what they found yet on the 12.5-year data. So they look at, they're looking for a common red noise source. A red noise, like I said, is low frequency. So it's a power law. In this case, it's like 13/3. It's a power law process that is correlated, that's seen among all these pulsars. So they have seen something. There is very strong evidence that something's there, but it's insufficient for them to declare that it's consistent with general relativity for a gravitational wave, because they need this quadrupolar signature, which they're not seeing yet. And the nanograph findings agree with Parks and the European set and the other groups that are all kind of working together, sharing their data. And so they do see something, but it's not they can't claim yet that it's gravitational wave. So what I'm really looking at more is just individual pulsars. In fact, I'm just going to be, the rest of the time, I'll just be looking at 3 individual pulsars, doing narrowband timing studies. So narrowband in this case means that they basically, at Green Bank, the Green Bank telescope and Arecibo, they actually have wideband receivers. They collect the data in very wide chunks at a time, but then they chop it up into narrow subbands. And by chopping it up into narrow subbands, they have basically simultaneous time observations at different frequencies, and that lets them identify and remove the dispersion, the propagation effects through the ISM, interstellar matter. So that's all that narrowband means is, yeah, you started with wideband, but they chopped it up into little bitty bands. And again, I'm not doing the full PTA. If you actually want to do studies for the gravitational wave, you need to look across all of the pulsars and not just look at a few of them. So for the timing analysis, I'm using a program called Pint. So if you've done pulsar timing, like with Presto, we tend to use a package called Tempo, which again was Joe Taylor, still Joe Taylor's Fortran, that's still in use for the timing. There's a newer package called Tempo 2, which is used with a PS archive package. It's in C++. Now Pint is the next generation of timing package. It's a Python package, and it's much easier to use. I found it very easy to use. I run it on a 16-core Ubuntu computer. Then I'll talk a little bit more about the Bayes noise modeling in a minute, and that's by a enterprise package, and that's on a 32-core Ubuntu machine. So Nanograv has made all of this. That was my fault. I got carried away on the cursor. Nanograv has made all this available on their website. So the code is at GitHub. So Pint and Enterprise and all the other code is on GitHub. Then the data itself, the TOAs are in models called .time, and the timing models are .par, which stands for the parameter. And if you go to the Australia national site, ATNF, they have .par models. They're simpler ones, but that's where you start with a .par that's published, and then you start adding in your model parameters. But again, you can get that data set from Nanograv. If you want the raw data, the very raw data, the FITS files, the calibration files, everything they've collected is at Globus. Globus is run by the University of Chicago. Anybody can log in there and you can download data all day long. So the process is I start with these time models, the time files and the parameter models, and all their data is calibrated. To get the residuals, I use Pint. I use a generalized least squares fit. So I'm fitting the model to the data, and Pint will generate these residuals and the plots, and it generates the model updates. And you can decide if you want to accept the model update or not. I did compare Tempo 2 with Pint, and they're very similar, almost the same. They've done extensive studies. There's slight differences between Tempo 2 and Pint because, well, one's Python's, one's C++. They're completely independent codes using slightly different algorithms, but very close in results. For the data search here, if you're searching for a gravitational wave, then you have to incorporate all the noise components that we talked about before in your model, all those uncertainties, into what's called a Bayesian joint probability distribution. So you're no longer thinking of a point solution to a problem. You're ending up, your solution is a probability distribution. You can think like a Gaussian curve, but it's multidimensional. You're not in one dimension anymore. It's very highly dimensional. And so this enterprise tool is set up to run all these Bayes models. And you know, I ran some simple cases for one pulsar, and it would take 12 hours on this 32-core computer. And at the end of 12 hours, I found out I didn't know how to do the modeling. I had bad results. I got to do it again. So it takes quite a bit of horsepower to do that. But the Bayes inference model accounts for the uncertainties in the search. And the noise is modeled as Gaussian. So you set up the noise as Gaussian. There's the white components we talked about, your radiometer noise. And then you have the red components, which is the low frequency noise. And there's these models for each receiver. The red noise is modeled. And so this is when you're doing Bayes methods, you have to specify what your prior distribution is. You have to tell the model, tell the code, what the distribution is beforehand. And in this case, it's logged uniform for the red noise. The white noise is just uniform, just means a nice Gaussian. And then the posterior means your results. And the distribution is sampled by this MCMC. So as soon as you see the words Monte Carlo, you realize it's a simulation. So this is a very large simulation, a multi-dimensional simulation across all of these receiver models. And you're simulating data for these 12 years, a lot of data, a lot of parameters. It's too much to search through. So they have a statistical method called Markov chain. So the Markov chain is just an optimal method of searching through all the data in your Monte Carlo simulation to get you some results. So that's the process. Now, the first pulsar I did was 1937 plus 21. I picked a few of the brighter pulsars in the pulsar array, partly because amateurs can detect these. I know Wolfgang has detected this one. I believe we could at Haswell. We haven't tried this one yet. It has a period of 1.5 milliseconds. We've detected a pulsar down at 4 or 5 milliseconds, and we've detected pulsars just a little bit above this. I forget, 14 or 15 millijanskis. So I think this is something we could collect. It would take several hours of collection. But since I didn't have the data from Haswell, what I did is I went to the Green Bank Observatory. So this GBO is not the GBT. So GBT is the big dish, and the GBO is the small 20-meter dish that we have access to through the SARA account. And in this case, I just went back through some of their archive data and found that Nanograv had used the GBO initially for some experiments. So there's a ton of data there. And this shows this pulsar. You look at the period derivative look all right. You can see the dispersion's good, except you notice it's like, oh, there's two pulses. Well, that's because some pulsars actually have a primary pulse and a secondary, it's called interpulse. So to confirm that, I went to the Nanograv data because they have very nice data. This is from their polarimetry studies for their 12-year data. And of course, it shows a very nice, strong pulse. They also show the Stokes profiles. Red is linear and blue is circular. This is the interpulse over here. So that matches what we see here from Green Bank. And then something that has been showing up in their data now that they're doing these very longer collections with very large telescopes. This black arrow, it takes good vision, but you might see a little bump here, just a slight little bump. They're calling it a microcomponent. So it's a microcomponent that's showing up in several of the pulsars, and they just arbitrarily defined it as, I don't remember if it was 1% or 3%, but a very low, something that's not at the peak, but it's 1% below the peak value, but it's consistently there. So it's something that's above the noise, but it hasn't been strong enough to show up much yet. So it's one more thing they found is a little bit more scatter or something there. So this was my starting point. And we're doing the timing studies. So on the left is the phase residuals, and on the right is the time residuals for the same data. So I plotted the phase and the time residual. So this is the observed minus the predicted pre-fit. This means I haven't run any fitting yet. This is just as I get the data. And the residuals on the order of plus or minus 4 microseconds. And you think, well, it kind of looks like a sine wave, except you got this broad gap in the middle, so that's not really a sine wave. And again, this is two telescopes, Arecibo and Green Bank Telescope, GBT. Arecibo has much better resolution. It's much more sensitive than Green Bank, so the error bars don't even show up for Arecibo. They're small. So then I run the post-fit. So what this means is I ran Pint. I did the fitting of the data. I'm sorry, I'm fitting the model parameters to the data. And I get an RMS down about 1.5 microseconds. Some of the data is flagged as bad, didn't meet the calibration standards or whatever, the data is tossed out. Oh, and the thing I didn't mention on this one, the data was too much for me to look at. I chopped it down to just 1400 megahertz plus or minus 4 megahertz. So I just took a narrow band around 1400 just so I could look at the data without, just filling up the plot. But when I ran the fitting, I ran the full data set, which was 17,000 residuals over the 12 years. So the next step then is you go run the Bayes modeling. So you transfer your model and everything over to Enterprise to run the Bayes model. You go run that. There's not a lot of pretty charts that you can bring back. You bring back your the parametric values for your white and red noise models, but then you go ahead and plot the residuals again anyway. So that's what this chart is. This is the summary chart for this pulsar showing the residuals. And I'm using the residuals as plotted by Nanograv. That's why I've got the NG up there, because my residuals didn't come out quite this nice. They got very nice ones. The main reason being they subtracted out the linear and quadratic terms across all of these because those are covariant with the pulsar itself, the pulsar orbital parameters. So they're getting rid of all known parameters to make the residuals as small as possible. The top one is the variance in dispersion measure. And you can see over time, again, this is 12 years along the bottom. So the horizontal scale is 12 years. The dashed lines is where they did major upgrades. So the A means Arecibo, and so it's either Arecibo or P for Puerto Rico, and then G is for the Green Bank when they've gone through major upgrades into the receivers. That's all those dash lines mean there. So that's the top one is the variance in dispersion measure. Next is the plotted all residuals. Well, they had the same problem I did. It's too much data to look at. The data looks fuzzy here because there's too many data points. The colors are different frequencies for the different receivers, so it's different frequencies. So they did an averaging technique. They're basically sampling and averaging to get this middle plot. So it's less data to look at. They still want to see the trends. They're interested in the trends, not in the individual data points. Then the bottom one, sorry, my fingers. The bottom one shows what they call the whitened residuals. So whitened residuals are taking the averaged residuals that you have here, and then they subtract out the red noise model. The red noise model is what comes back from your Bayes modeling in Enterprise. And in this case, this particular pulsar has a high red noise model, meaning the red noise exceeded a threshold of what they expected and exceeded threshold of others. That doesn't mean there's any gravitational wave coming from there. What it most likely means is there's still unmodeled effects probably in the dispersion measure. So a high red noise model on an individual pulsar likely means that, well, you got to do some more modeling on your dispersion measure or something else that you haven't accurately modeled. So I'll quickly go through the other two. They look quite similar. This was J1713 plus 0747. Nice strong peak on the profile. The pre-fit and the pre-fit phase and time plots look completely different. And I don't know why. Again, I'd narrowed it down just to 1400 megahertz just to get a slice. But again, you can see the residuals were much larger before they upgraded the receivers. They upgrade the receivers and the residuals all get smaller. Again, this is a plot of the post-fit. After I did the least squares fitting of the model parameters to the data, throw out the outliers, and you get a RMS down here, 1.7 seconds. And then again, you go run the Bayes model to get your red and white noise models, and you do this plot again. So this is a different pulsar. So it's a different direction. The dispersion measure variance will look different. These residuals in this case are flat. The averaged ones are flat, and even after you subtract out your red noise model, it's still flat. There's no strong indicator of red noise model on this one, and the same on this one. So J2145 plus or minus 0.750. The Presto plot looks good from the Green Bank Observatory, except you notice, there's this big chunk here. You got a double peak or wide. What's going on there? So when you're doing Presto runs and you first see something like this, my initial thought is, oh, I didn't fold it at the right period. The folding period is wrong or something else is wrong. But the rest of the indicators are it's a good pulsar. You go look at the nanograph data. Sure enough, it's got a very wide base. This is very strange. You got what you expect for a radio pulse, but then you have the base of emission that's quite wide. So that's in the data. This one is fairly close, dispersion measure of 8. Signal to noise, the flux at 1400 megahertz is almost 5 millijanskis and 16 milliseconds. So it's a little bit slower one. Then same process. I look at the 1400 megahertz data. In this case, Arecibo did not collect this one. This was Green Bank telescope only. So this is just the 100-meter dish collecting over the 12 years. And there's always gaps. Green Bank was down for a year. They had to do some major repairs on it. When they change receivers, it's down. There's other priorities. So that's what the gaps are. The same thing with the gap in Arecibo data. They'll have a major hurricane or earthquake and the telescope was offline for 9 months or a year or something. But when you're collecting data for 12 or 20 years, that can get averaged out. Then again, I go do the pint process to model the parameters, adjust the model parameters, throw out the outliers. Again, it's flat with a small RMS, and then this is a different pulsar, so it's a different direction. The dispersion measure variance model will look different. Some of these jumps are unexplained. It's in the data. Does that mean it's real? Swirling cloud of gas. It's a lot of questions there. Then they average down the data. The residuals are getting very small, and then they subtract the red noise model from the whitened or from the average to get the whitened, and it's nice and flat. So again, no big red noise model there. Those are the 3 pulsars I did. I did not even want to think about trying the whole pulsar timing array. So some future possibilities. The 15-year data had been scheduled to be released already, but it hasn't. And one of the presentations I looked at indicated that they're having some issues with the wideband data. So they're still working on the 15-year data. It'll be released soon. At some point in the next 5, 10, who knows how many years, they fully expect to make a big announcement that they've detected gravitational waves in the radio band. Meanwhile, other things so yeah, I don't think I'm going to do the full PTA. I don't have the computer or the mental bandwidth to do that. Just doing single pulsars was fun. One thing I would try is what I've talked about here is doing these explicit parametric models for the dispersion measure and all the physical factors. Well, there's another way to decompose data. You can take your data set and run a principal components analysis, which is basically an eigenvector decomposition. That decomposes your data into mutually orthogonal basis vectors. That it's an efficient way to decompose data. It's used in machine learning a lot. The disadvantage of it is it's very hard to assign any physical meaning to these eigenvectors. So even though you've got a good decomposition of the data, it can be hard to really attach physical meaning to what your components are. But it does help you if you're trying to come back in a month or a year and run the same pulsar. Then you can see, well, what's changed here. So it's an option. And then there's a lot of other things you can do. You can study the Keplerian orbital elements from this data and the relativistic ones. So there's quite a bit more to do. But like I said at the beginning, this is just the exploration of it. So if you've got this, these are the papers and presentations and the sources that you can look at. So are there any questions?
Dan, can I ask a question?
Sure.
It's I tried to do some pulsar timing on the B0329 plus 54, the one that you mentioned, and there was maybe over a month or so, data from a month every couple of days. And I found that the residuals were quite large that I had, something like a couple of milliseconds. And it was sort of scattered around, so it was not something where you could adapt a model. You had a comment about the mode changing of the pulsar. That made me think, do you have any idea how much that affects the timing? Could that couple of milliseconds be explained by a mode changing of that pulsar?
Yes, I believe so, because when they are using these millisecond pulsars, they use the millisecond pulsars because they have a very narrow, steep pulse, and they can easily find the peak of the pulse. Whereas if you've got mode changing, you may have a harder time finding the peak of the pulse sometimes.
Yeah, I was looking for an instrumental artifact, so maybe I just revisit that and just try another pulsar and see whether I get better results.
Yeah, I'd like to know how that turns out. I haven't tried that yet. That's what I want to do. We need to get our data calibrated, and then we can try that. Any other questions?
Yeah, Jim Van Proyen here. What are you using for your processing? What kind of computers?
They're for the timing, I'm using it's a System 76 Linux laptop, 16 core, and then for the Bayes modeling, it's a desktop with 32 core. It's another System 76 Linux machine.
Okay, I'm experimenting with Turing Pi. It's version 1s and version 2s, so I'm just interested.
Okay, all right.
Thank you, Dan. Thank you very much.